the last lecture, we discussed actually some different concepts of the atomic structure or the atomic view of the matter. And later on, we reached to the Rutherford's model. Sorry. The painting curves. So in Rutherford's model, what Rutherford actually did, he proposed that Rutherford proposed that the electrons which are negatively charged electrons, they move in Coulomb field of the nucleus in orbits. So this orbital concept was from the actually in the orbit. It was proposed by Rutherford that electrons move in Coulomb field, so Coulomb field of the nucleus, and in orbits like a planetary system, That means just like the planets, they are moving in their orbits. Same, these electrons, they are moving in their orbits, and under the Coulombic field of the nucleus. That means nucleus is positively charged and electrons are negatively charged. So that force of Coulombic force between the positive and negative charge, they hold it, and that allows it to move about it. So, and then according to this postulate, if we analyze this postulate further, we will see that a particle, if it is moving on a curved trajectory, on a curved path, and it is trajectory path, so it is, here is the nucleus, if this is a nucleus, and there are the electrons which are moving here in these circular orbits. So that means if we have an electron which is moving and continuously moving, so whenever it reaches, there's a Coulombic field in this direction. So that means this charge will accelerate. So the electrons will be accelerating when they go on moving in the circular, these orbits. Circular was an assumption actually, or elliptical, and accelerating. They are accelerating, and any charged particle which is accelerated will radiate an electromagnetic waves. That means they lose energy. So that means this is from classical electrodynamics, that any charged particle, if it is accelerated, it will emit an electromagnetic radiation, electromagnetic waves, and hence they lose the energy. Since they are emitting the radiation, that means they are emitting some part of their energy. So when they are emitting some part of their energy, they lose this energy. And Newton's laws, or the Maxwell's electromagnetic radiations, if you analyze them more deeply or thoroughly, these are all the classical laws. Maxwell's electromagnetic radiations equation, the equations which you had given, these are classical equations, as well as the Newton's laws of motion as well. In the time span of, they have calculated this, that in a minus 10 raised to minus 10 seconds, all the energy of the atom would be radiated away. That means since every electron will be orbiting a nucleus, or it will be moving in a circular path around the nucleus under the Coulombic field, since it will radiate the electromagnetic energy and it will lose its energy, so each electron will be lost in the form of an energy. So in a time span of this much, very small time span, all the energy of the atom would be radiated away, and the electrons would collapse into the nucleus. Since electrons would have no kinetic energy, then they will not be able to move. If we assume that Rutherford was 100% correct when he proposed that postulate. So according to that postulate, when we analyze it more, we observe that in this much time span, the energy of the atom would be radiated away and the electrons would collapse into the nucleus. So there was no electron, no atom, no nucleus. So all the atoms. So this was actually contradictory. So this was a contradicting postulate. The another drawback or the limitation of the Rutherford's model, that there's a central part nucleus which is concentrated mass, and it's at the center. Electrons are orbiting in circular orbits under the Coulombic field of the nucleus. So this postulate led to the another drawback of Rutherford's model. That is, it was not able to explain, not able to explain atomic line spectra. Line spectra means line emission spectra as well as absorption spectra. So that means when a atomic gas, that means a gas of hydrogen atoms or a gas of helium atoms, that means the atomic line spectra, it was not explained according to by the Rutherford's model. That means using Rutherford's model, it was not possible to explain the origin. That means if this is a photographic plate, you have some bands here. These are some bands here, and there's a missing line. There is again another band, again another band. So these bands, so there are lines which are visible and some lines which are missing. So that means they form a line spectra, line emission or the absorption spectra. So it was not possible to explain from this Rutherford's model. Then what happened? Then actually Bohr started working on it. Before Bohr could start working on it, people tried to study the spectra of hydrogen. Spectra, that means the distribution of frequencies of the wavelength with incident frequency or with incident energy, how the output is varying when we shine some external light, white light. White light means that we have all the wavelengths in the single light. So that is why it is white actually. So when we pass,
repeat कीजिए.
okay, यहाँ तक ठीक है, यहाँ तक. So is it okay up to here?
Yes,
Drawbacks,
sir.
drawbacks. Okay. So the spectra of hydrogen atom was studied by different scientists actually, and before that spectra was completely studied, people tried, or scientists tried to see the different components of a white light. White light means that we have all the components of the light. That means all the wavelengths, like in the visible spectrum. That's a white light, the visible shape, WIB-GAR, which you have studied in your earlier classes or in your higher secondary classes. So white light was actually resolved into separate lines or the constant colors or constant wavelengths actually. And the first person who done it, he was Isaac Newton. So Isaac Newton was the first person to resolve the white light into separate lines. And how he done it? He simply brought a prism and allowed the light to pass through that prism, and he saw a rainbow, that spectrum of different colors. So Isaac Newton done that at first. Any issue? आपकी आवाज कट हो रही है. So your voice is breaking actually. Whoever is talking, voice is breaking.
नहीं, मुझे लगा और okay.
Okay, if any issue is there, please write a message to me because the voice is breaking. And in 1957, there was a person whose name was T. Melville. He showed that light from incandescent gases, which are the gases are there like halogen gases. These gases were composed of large number of discrete frequencies. That means when those gases were ionized and the radiations were collected on a photographic plate, they saw that this light was composed of large number of discrete frequencies. They were actually discrete liners. Those liners were called emission liners. And these emission liners were resolved with respect to frequencies. From the gases like halogens. So these were considered, so that means the gases, the liners were discrete in nature. And this was studied in 1957. 1957. It was also proposed that atoms, when exposed to white light, can only absorb light at certain discrete frequencies. That means if we have an atom here and we shine some light H nu, so it absorbs this light which is coming, but at certain discrete frequencies. So at if you shine a white light to the atom, it is not possible that all the wavelengths will be absorbed by the atom. Some certain discrete frequencies, which are called as absorption liners actually, those will be absorbed by the atom. And later on, after that, then when people studied all these, then the progress was made. When use of gratings was, people used gratings. You know gratings, diffraction gratings, which are which
Yes,
are
sir.
spaces of the order of the wavelength of the light. So when the gratings were discovered, people studied the spectra, and it was easily observed that this spectra is resolved into the number of liners, different liners. A line spectra was observed by the use of gratings, and this was all happening at the end of the 19th century. At the end of 19th century. That means 1870s to 1900, like this. 19th century. C.R. Kirchhoff, what he saw, he observed that, he showed that only certain definite frequencies can be radiated or absorbed by a given element, and emission frequencies coincide with absorption frequencies. This is one of the important points, that only a certain definite frequencies can be radiated or absorbed. C.R. Kirchhoff showed that only a certain definite frequencies can be radiated by an atom or absorbed by an atom or by a given element, and the emission frequency coincide with absorption frequencies. That means whatever incident here H nu, we will get the same frequency in the output from the atom, from the element. So Kirchhoff showed it that we have only certain set of frequencies, or the discrete definite frequencies, which are radiated. They are also absorbed by the given element, and emission frequencies, which we saw in the spectra on the emission after the emission by the element, they coincide, they are same as that of the absorption frequencies. So this line spectra actually, which was studied before the discovery of this, before the Bohr's theory of hydrogen atom. Bohr's theory of hydrogen atom was not at this stage developed. It came later after this. Before it, the line spectra of hydrogen atom was studied by the people. The line spectra of the hydrogen atom. One is the Bohr's theory of hydrogen atom, another is the line spectra of the hydrogen atom. So Bohr's theory actually explained that how those line spectra originate. That was explained by the Bohr. And line spectra was studied individually. It was studied on the gases, on the experiments, but there was no definite theory. So line spectra actually, it was important. It was of great importance. How? Because it is the only means by which the presence of particular element in the sun and stars was determined at that time. Line spectra. So line spectra, that means every atom or an element or the atom of an element has its unique line spectra. Line spectra means that the emission lines or the absorption lines at a certain frequencies. So that means the absorption lines or the emission lines can occur at a particular value of the frequency or the corresponding wavelength or the wave number as well for a particular given element. So if you have hydrogen, there will be a line spectra at a particular value of the frequency. But if you have helium, this nu will change, but it will be unique to helium. This nu for hydrogen will be unique to hydrogen, and here it will be unique to helium. So it is not expected, or it's not possible that the frequency at which helium atom absorbs, the same frequency is absorbed by the hydrogen atom. It is not possible. So it is unique to each element, this line spectra. With this uniqueness, if we have a line spectra and we know the values of the frequencies or we know the values of the wavelength, we can say that it corresponds to a particular atom or it corresponds to a particular element. So that is how it was of great importance, this line spectrum. And it was used to find the elements in the sun and stars, because the radiations were coming from the sun and stars. So they resolved those radiations actually. And while working on this, J. Balmer, while working on the line spectra of the hydrogen atom, in 1885, he showed that, or he proposed that, what Balmer proposed that, he proposed that the frequencies are a series of lines. So it was not a single line. It was like this. Series of lines here. One, there was another series of line like this. There were 3, 4. I'm not concerned with the number at this time. I'm just showing it what Balmer means at this, by this statement. So he showed that the frequencies of a series of lines, that means frequency of this series, frequency of this series, frequency of this series, frequency of this series. So the frequency of series of lines in the visible part of spectrum of atomic hydrogen. So since they studied the hydrogen atom spectra, and he said that, he proposed that the frequencies of a particular series, this, or this, of an hydrogen atom, the atomic spectra of the hydrogen, were among those, these were those lines, these spectral lines, and these lines were given by the frequency of these lines, those, it was among those lines where the frequency nu AB was given by the formula. You all have seen this. Where N is 1, 2, 3, and B is equal to 2, 3, 4. This was later proved that what N is actually, at this time N was not known. So people named on them that it is indexing. They indexed it as per natural numbers, these 1, 2, 3, 4. So they said that these spectral lines, the group of these lines, the group of these lines, the frequencies of these lines of these groups were determined from this equation. So that means they said that it was coming from some, it is a line 1, line 2, so it is between these two lines. And these are simply integers, and R was a constant actually, which was later on derived in an expression from Bohr's theory. It is a constant given, called as Rydberg constant. It was later on called as Rydberg constant. So what Balmer proposed? The Balmer proposed that the frequency of the series of lines in the visible part of the spectrum, this was in the visible part, not in the other IR and UV. There is a whole spectrum, IR, UV as well in the hydrogen. So in the sun, when the sun emits the spectrum in that visible as well as IR and UV as well. So Balmer proposed that in the visible spectrum, we have those, the lines which are in the series of that different series of the spectra, those frequencies are given by this empirical formula. He does not derive it from anywhere. It is an empirical. He just put up the values that if a line is coming between some two different points here and here, he named it one. So if it goes from this point to another point, he named it another by like this. It was later on that these are the energy levels and the orbitals actually n is a quantum number. So that we will see later on. But at this time, the quantum numbers were not known. So people were not aware about where from, what is the origin of, what is that n exactly. And NA and NB, these both were greater than 0, that is positive. And this NB was greater than NA, that is the only case when NA and NB are greater than 0. This whole nu will be positive. And R was a constant. So this was the case for the visible spectrum. This is the line spectra of the hydrogen, and it was visible spectra. Now, in case of UV visible regions, frequencies are represented, that nu or represent is usually represented by converting into wave numbers. And a wave number nu bar is reciprocal of wavelength, which is nu by c. C by nu is lambda, actually 1 by lambda is nu by c.
और क्या है convert wave numbers में?
वेव फ्रीक्वेंसी जो स्पेक्ट्रा आते हैं यूवी विजिबल जो विजिबल रीजन में, स्पेक्ट्रा को हम जैसे हम प्लॉट करते हैं spectrum, we have some spectrum, for example these are the emission lines, this is spectrum, so we write on the x-axis wave number nu bar. This wave number is nothing, it is actually reciprocal of lambda, wavelength. So spectra in the UV visible regions, the frequencies actually are converted into wave numbers. This is the frequency nu, this is the speed of photon which is absorbed by some atom, and this lambda is a wavelength of that particular photon which has been absorbed by the atom or emitted by the atom. So nu bar is the wave number. This is just a parameter in which the spectra is represented. And experimentally, theoretically, the wave number, this Rydberg constant, it was 109,677.58 centimeter inverse. So it has a unit of wave number. Okay. So this nu AB here actually is this. They have converted actually this frequency nu AB, if you write it AB, they have, it is V bar, they have represented the spectra as represented as V bar in the this, what it is called reciprocal of the wavelength or the wave number. If we have an IR or microwave spectra, these are represented in megahertz range by megahertz. So wave number has a megahertz range, and wave number is represented in centimeter inverse. Its unit is 1 by lambda. 1 by lambda is inverse of distance, so that is 1 by that is centimeter inverse, and it approximately comes out to be 10 raised to the power 14 by 3 in times new frequency megahertz. 10 raised to the power 12 is actually of megahertz. 14 is actually of that converting centimeter into SSI unit meter. That 2 comes here actually, that's why it comes 14, and they have converted it into megahertz range, where velocity of the light has been taken as V, 3 into 10 is about 8 meter per second. This was one of the, this Balmer, he proposed that this is a particular one of the series of the hydrogen atom, and which was later on called as Balmer series actually. And however, the Balmer series, it was shown that Balmer series explains as well the complete spectrum of the hydrogen atom. So Balmer series was able to complete spectrum of the hydrogen atom. And in hydrogen atom, how they named this series, for example, in hydrogen atom, how they named it, when Na is equal to 1, it was called as Lyman series from that expression which we derive, which we have written above. When Na is 1 and it lies in the UV region of spectrum, it so this when Na is 1 and B is then 2, 3, 4, and B is usually greater than Na. And for this, when N is 1, it is called as Lyman series, and it lies in the UV region of the spectrum, whole that spectra, electromagnetic spectrum. The lines are, for example, I have drawn it above. They were treated as alpha, beta, gamma, delta in the Greek letters, in the order of descending wavelengths, decreasing wavelengths. So we decrease the wavelength, they were naming as by alpha, beta, gamma, and etc. So this was first in this whole, according to this expression which was given by the Balmer. So for the first, when Na is 1, it was named as Lyman series and determined by this. So Lyman series was denoted by L. So we have L alpha, L beta, L gamma, L delta, etc. What there are the different lines in the Lyman series. L alpha, L beta, L gamma are the different lines in the Lyman series. And Lyman series is a group of frequencies which are closely spaced, and these are represented in the decreasing wavelengths. For example, when for Lyman series, when Na is equal to 1, this is a given, this will remain fixed, and B is equal to 2, if the line which is measured, the wavelength of that line is particular 1216 angstrom. And this line was called as L alpha. So the first line of the Lyman series is L alpha with the wavelength of 1216 angstrom. Similarly, when NB is equal to 3, there are different lines, there are another values you can calculate by putting up the value of R Rydberg constant, which is given above. When you put that Rydberg constant, you will find when NB is 3, NB is 4. When you reach NB is infinity, that means the series limit. When we go up the end, that means, and there's a series limit, the last line in the Lyman series, this will give you the last line in Lyman series. This is series limit. It occurs at 912 angstrom, this series. And this is how we determine this. This is a Lyman series. Similarly, there was another series, and yes, there was another series when NB is equal to 3. This was named as H series, where we have H alpha, H beta, H gamma. So this is L beta. N equal to 4, this is L gamma. But we are series limit, we don't have any line which is less than 912 angstrom in the Lyman series. This was this series, H series, or the H alpha series, H series. It was investigated with J. von Fraunhofer in solar spectrum. The strong line in this Balmer series, or in this series, N equal to 3, NB equal to 3, was at 6563 angstrom. And we can draw it, how you draw that spectrum. If we have one line here, another here, we have H gamma, H delta. There are more series to this, more lines in this H delta. And there is a series limit here. This is the series limit. This series limit occurs at below 30,000 angstrom. So if you draw the wavelength here, this is 30,000 angstrom. This is, I will write the name here. This is H alpha, H beta, H gamma, H delta. These are of these are other lines. These are very small in energy and they cannot be observed clearly. So these are drawn as like continuous here. And this is the series limit which occurs at this falls in the UV region. This is also UV. Okay, ultraviolet. This is blue region of the spectrum, and this comes into the red. And this is 30,000 angstrom here in the this UV region. So we have, this is wave number, it is 15,000 here. This is 20,000 centimeter inverse, and then there is 25,000 centimeter inverse. This is 30,000 here. Centimeter inverse, not angstrom here, sorry. Because spectrum will be represented in wave numbers. So next numbers in the series of this is NB equal to 4. This line occurs at 4861 angstrom. And this is for the blue. You can convert this actually into the wave number and the earlier expression. And B is equal to 5. This occurs at violet. And the series limit occurs at series limit 3646 angstrom.
सर ये सीरीज लिमिट क्या होता है?
Series limit होता है that the particular series and has a last line at this particular value of wavelength. Last line.
Okay, sir.
Yeah, it's like this here. So if I assume that this is a particular series, so this is a Balmer series or the H series, this is the last line. So we can't observe any other separate line here below the value of this 3646 angstrom. Here we can measure a line which has a wavelength of 3646 angstrom, and we cannot measure another line which has a frequency, this wavelength less than this. That becomes its limit. So the another series in this Balmer, according to Balmer's spectral analysis, was the Paschen series. For it was, and it comes out in the IR region with Na equal to 3. Yes. And it starts with a line at 18751. We will study in, we cannot expect, we don't actually go into the whole detail of the hydrogen spectrum, but we have to just give a brief idea and how Bohr modified that earlier theories of the hydrogen spectra to reach to the quantum numbers actually. So we have to start basics from actually quantum numbers. Then there was a bracket series with Na equal to 4, and it starts at 40,500 angstrom. Then there is P fund series. These are different series you know in the hydrogen atom actually. And for this, Na is equal to 5 at 74,000 angstrom. This is 1000 here, angstrom. That work also showed that this was for that different series from as per the Balmer's theory and Balmer's empirical relation actually, which he derived, which he put up there. Is he put up that empirical relation. And after seeing this analysis by Balmer, Rydberg said that for other atoms, these were for the hydrogen atoms or the one electron atom, generally hydrogen atom is then treated as a prototype for all the one electron atoms. like helium 1 plus, lithium 2 plus. Those all become one electron atom. And what Redberg said, he said that for other atoms, and particularly for alkalis, actually, frequency of lines actually they can be represented by by a difference in what they call as term. So term is actually terms. It is actually the ratio of R by Na square.
Yes, sir.
Okay. So what Redberg said about actually other atoms, particularly for alkalis, that frequency lines could be
सर ये
represent.
टर्म्स जो है ये फिर से
हाँ,
बोले
terms actually.
टर्म्स.
Yeah, what they do actually, they treat it NB tends to infinity. That means as for higher lines, for higher index of Na and Nb. So when we have Na, we start from the Na and reach up to different Nb values. Then if we treat Nb at infinity, we are left with this term, which they call as terms. And for other elements, higher Z, that means generally for alkalis actually, the frequency of the spectrum, which we observe for those, theoretically they said that theoretically it can be represented by the difference term Tn. What was Tn actually? Tn was actually R by this n plus alpha. It is not infinity, it is alpha, where n is 1, 2, 3, and alpha is a constant for each particular series. So they have set up a particular constant value of another series. They named them this series differently by particular constants, and b is infinity actually. So n is 1, 2, 3. That means we have these different lines. We have Na here. These are all the Na, and Na was actually n is equal to then this. If this is a particular series, in this n there are different lines here. Then they added this alpha. Alpha is n plus 1, n plus 2, and there's a constant for each particular series.
सर इसको रिपीट कीजिए, समझ ही नहीं आया.
समझ नहीं आया? Okay. What in above what we have done, we have seen that the atomic spectra of hydrogen atom, the hydrogen atom actually was given by R 1 by Na square minus 1 by Nb square, and this was given by Balmer. Actually Balmer, and those names, some series were named after the Balmer, so that was a Balmer series actually, and there were named other series by changing the values of Na to this, telling Na with different values of Nb. So for a particular value of Na, we have different values of Nb. But what about the other atoms? For other atoms, Redberg said that theoretically that we have the difference term. Difference term means that, for example, nu12. Nu12 is the frequency of a line. Nu12 is the frequency of a line in an alkali atom or in any other atom other than hydrogen, which has a term that is T1 minus T2, but T is equal to R by Na square. Simply, this is it. If you have studied Rittis combination principle, have you heard the name Rittis combination principle? So Balmer said, this Redberg said that the frequency of a line which is emitted from a particular atom other than hydrogen atom, they have the frequencies which can be represented in terms of this expression. This is called terms. T equal to R by Na square. R is the Redberg constant. This Na is the index actually for a particular line. So for first line. So there was no Nb actually tends to infinity, so that 1 by Nb becomes 0 in the above expression. In the Balmer's expression, which is proposed by Balmer. So new 1, 2. So this was a difference between the two different lines. If we have a line here, I can write this line. So if we have NA here, and this NA line, it corresponds to, for example, NA is equal to 1. For another, any other hydrogen, other atom other than hydrogen. And NB is infinity. So we don't know, there is some line which occurs and it goes from one level to another level. So this line was just T, this R by NA square, and if there's a line in between this another line, then the frequency of this line, frequency between these two lines, this gap, or the absorption frequency or the emission frequency, that was given by T1 minus T2. So if it is nu equal to 2, nu equal to 1, and this is given by R by NA square. This is also given by R by, yeah, for this NA, this will be NA will change, NA will change here. So it is Na plus alpha actually, which they said that it is a constant for a particular series. So the frequency of these two lines will be determined by T1 minus T2. So T1 is actually this R by Na square and R by Na plus alpha. So there is some index which has been put up at the next level. And if we have another level, nu 2, 3, that is between the second and the third, is T2 minus T3, then the frequency, there will be another frequency, T1, 3. So according to Ritter's combination principle, there will be another line, nu 1, 3, not T1, 3. This is nu 1, 3. So nu 1, 3, and it is equal to the combination of T1 minus T2 plus T2 minus T3. This is the combination. That's why it's called the Ritter's combination principle, and it is theoretically equal to T1 minus T3. So this has been theoretically actually examined with the experiment. And Ritter's combination principle states that if lines are at frequencies from Ritter's combination principle, so if we have lines at nu ij and nu jk, so if we have the two frequency lines, one is at ij and jk, they exist in the spectrum with j greater than I and k greater than j. J greater than I, k greater than j. Then there will be usually another line at Vik, where Vik is equal to Vij plus Vjk. This is a principle, it is combination principle. So there will be another line, but all the lines will not be possible. All lines are not possible because of some selection rules in some spectra. If we use this Ritter's combination principle, those alkali atom spectra, so this will be not possible to observe because of some selection rules. So I think it is today, it is enough for today. Okay, we will leave here and then we will start the basic Bohr's theory for next lecture.